Hello and welcome to this lecture. So, we saw earlier that every subspace now has a orthonormal basis. I am just formally calling it as a property. It is very easy to do. You just start with a spanning set to go to a linearly independent set if you like, and take that linearly independent set, apply the Gram-Schmidt orthonormalization process, out comes an orthonormal basis. Remember in the Gram-Schmidt process, in every intermediate step the span matches. Okay, so that is also a very crucial argument. So, the proof here is very easy, and that fact that the span matches in every intermediate step gives you what is called Schur's theorem. Schur's theorem is very nice. It says for any operator t in Cn to Cn, okay, the complex is important here, there exists an orthonormal basis with respect to which the matrix of T is upper triangular. Now, you may recall the other result we had, hopefully you recall this. For any operator T, there is some basis with respect to which T is upper triangular. You do not need any inner product for that. Okay, so we can use the eigenvalues smartly and manipulate and get an upper triangular matrix. But it turns out if you use inner products, it is not just any old basis with respect to which matrix of T is upper triangular. There is an orthonormal basis with respect to which matrix of T is upper triangular. Now, that is very useful, in particularly when you deal with computational problems. Okay, so consider the basis with respect to which the matrix of T is upper triangular. We know already there is some basis. Using eigenvalues, we can find this basis, eigenvalues and eigenvector. You can find a basis for which matrix of T is upper triangular. Then you do Gram-Schmidt on the basis. Okay, this is just a proof sketch. I am not writing down the thing in full detail. You can do a Gram-Schmidt on that basis. When you do Gram-Schmidt on that basis, you will get an orthonormal basis. The claim is, because of the spans, the way the spans work in Gram-Schmidt, the matrix of T with respect to this orthonormal basis remains upper triangular. Okay, so that part needs a little bit of writing down. I am not doing that in great detail for you, but this shows you the usefulness of orthonormality. So, you have an orthonormal basis with respect to which the matrix of any operator is upper triangle. Okay, so this is very useful property. Okay, so here is a little bit of an illustration. Maybe this property needs a bit of illustration. Okay, so you are asked to find an orthonormal basis with respect to which 2 by 2 matrices are upper triangular. Okay, so let us try the 2 by 2 matrix. 2 by 2 is very easy. I mean, finding these bases for upper triangular is very easy in 2 by 2. So, let us do that first. Okay, I think the case is 1, 2, 2, 3. Let us do 1, 2, 2, 3. So, if you do 1, 2, 2, 3. So, if you remember, to find upper triangular you need eigenvector, eigen values and all that. So, let us find the eigenvalues. So, you have 1 minus lambda times 3 minus lambda minus 4 is 0, right. So, that is the equation. So, you have lambda squared minus 4 lambda, is that right, minus 4 lambda minus 1 is 0. So, you are going to get complex looking answers for the for this. You will get 16 plus 4, yeah, by 2. So, it is 2 plus or minus root 5. Okay, I hope that is correct. So, it is 2 plus or minus root 5. That is the, I hope I got that right, 20 is 2 root 5, yeah, 2 plus or minus root 5, okay. So, now how do you find eigenvectors? So, you have to find eigenvectors. So let us say 2 plus root 5 you take, it is minus 1 minus root 5, 2, 2, 1 minus root 5, right, okay. Alright, so how do you find null space for this? First of all, this looks a little complicated to you maybe, but if you multiply these two, you see that the determinant is 0, right. So, if you multiply these two, you are going to get, it is actually root 5 minus 1 into root 5 plus 1, that is actually 4, and then 4 minus 4 is 0. So, this is actually something that has a null space vector. So, you can find a null space vector. So, how do you find a null space vector here? Let us do this. So, I need to take this times x1, x2 to be equal to 0, 0, okay. So, you will end up getting, so let me just do this in gory detail, 2 into minus 1 minus root 5 plus x1 plus 2 x2 0. So, you have your 2, it is not 2, plus 4, right. So, multiplying the first equation by 2. Second equation I am going to multiply by minus root 5 x1, and then just to check that things are working out okay. This should work out okay. Plus 1 minus root 5 into minus 1 minus root 5 into x2 0. So, these two will give you the same equation because this is equal to 4. Okay. So, it is okay. So, this is working out correctly. So, you can take x2 to be a free variable and not worry about anything else. So, or any way you can take. You can also take x1 to be a free variable, or let us take x2 to be a free variable. Look at the first equation, 2x1 plus 1 minus root 5 x2 is 0. So, you take x2 as a free variable u, and then your x1 becomes root 5 minus 1 by 2 times u. So, so the eigenvector corresponding to 2 of 2 plus root 5 is actually, so this u can be put as 1 if you like. So, you get root 5 minus 1 by 2 comma 1. Okay. So, you can also, you can do any scalar multiple of this. Just for simplicity, I will keep it as root 5 minus 1 2. Okay. So, that is my eigenvector with eigenvalue 2 plus root 5. Okay. So, you can also find the eigenvector for eigenvalue 2 minus root 5 and then go to a orthonormal basis here. So, the question asks you for something like that, but maybe I will do it. 2 minus root 5 is, I can put x2 equals 2, I would get x1 as 1 plus root 5. Okay. So, maybe root 5 plus 1. So, root 5 plus 1 2 and then root 5 minus 1 2. So, notice one very interesting, oh I am sorry, minus 2 here, sorry, did I get that right? So, let me just do that correctly. 2x1 plus 1 plus root 5 x2 is equal to 0. So, you put x2 as 1. So, you get x1 as minus 1 plus root 5 by 2. So, there is a minus here. So, you can keep it as minus 2 here. Okay. So, very interesting fact here. So, let us say this is V1, this is V2. Notice what is V1 comma V2, the inner product V1 V2, you get 0. So, do you notice that? Okay. So, you can see root 5 minus 1 into root 5 plus 1 is 5 minus 1 4, then my 2 into 2 is minus 4, it ends up being 0. So, these two vectors, eigenvectors ended up being orthonormal, okay, orthogonal, but I can make it orthonormal, right. So, I can define u1 as v1 by norm v1, and then u2 as v2 by norm v2. You can compute the norm, I am not going to do it for you, it will get some answer. So, you divide by something, so you will get the answer. So, this u1 by u1 comma u2 is an orthonormal basis. So, this has got distinct eigenvalues, two orthonormal eigenvectors. So, in fact, this matrix in this basis of u1 u2 will be diagonal. Okay. So, with respect to u1 u2, the matrix becomes diagonal with 2 plus root 5 and then 2 minus root 5 0 0, not just upper triangular, it becomes diagonal. Okay. So, some magic happened here. These two eigenvectors ended up being orthogonal, and that is not really magic. There is a structure in this matrix which guarantees that lambda squared minus 5 lambda, and then you have minus 2 is 0. So, the two eigenvalues you are going to get are 5 plus or minus square root of, oh my god, this is really ugly, 25 plus 8, that is going to be 33 by 2. So, you get 5 plus or minus root 33 by 2. Okay. So, it is really ugly stuff happening here. So, here if you find eigenvalues and eigenvectors, it does become diagonal, but you will not have orthonormality. Okay. So, maybe I should see if I can cook up a nice example where I do not have to deal with this stuff anymore. Let me just see, give me some time. Minus 6 plus 2 at the cloud, so it should be minus 12. So, I want minus 12 here. So, I should have here. 3, I should have 6. Okay, 2, 6, 4. Minus 12. So it will end up being, oh, it's not 5 now. Minus 6 plus 1 minus 6, you know, minus 10, so 5, okay, minus 10 now. This goes to 6. Okay, this works. I will change this example a little bit. Okay, so let's go to the second example, 1, 2, 5, 4. So we saw in the first example, some magically we got an orthonormal basis with respect to which this was diagonal. Let's try the second example, 1, 2, 5, 4. Okay, so slightly different from before. Let's try this one. If you try to find the eigenvalues here, you're going to get 1 minus lambda, 4 minus lambda, minus 10 equals 0. So this is going to be lambda squared minus 5 lambda, right? Plus 4 minus 10, so it's minus 6 equals 0. So here you get nice solutions. So you get lambda is minus 1 and plus 6. I think that's correct. 36. Yeah, that's correct. Minus 1, 6. So these are the two eigenvalues. You can try to find the eigenvectors corresponding to this. Let's find the eigenvectors corresponding to this. This would be so I need to solve lambda is minus 1, so it's 2, 2, 5, 5. Right. So this is my for lambda equals minus 1, this is my matrix. So null space vector eigenvector is just 1 comma minus 1, right. So that's very easy. Okay. So and if you put lambda equals 6, you're going to get the matrix minus 5, 2, 5, minus 2. So am I right? Yeah. So that's going to give you, it's going to give you an eigenvector which is what? Did I get this right? Yeah, this is true. So it's going to give me 2 comma 5, right? So 2 comma 5 will give you 0 here. If you want, you can normalize it, etc. So with respect to these two eigenvectors, the matrix for the operator, so suppose this is M of A, you can do SS inverse or whatever. So the matrix so suppose this is T, an operator T, which is represented by that matrix of T with respect to 1 comma minus 1 and 2 comma 5 is going to be, if you do 1 comma minus 1, so you can try that once again just to check that your calculations were correct. 1 minus 1 gives you minus 1, 1, so it is minus 1 times 1 minus 1, okay. So it will be minus 1, 0, and then if you do 2, 5, again you can check, it should come out correctly. It will be 2 plus 10, 12, 12 is I think 6 times 2, and then 10 plus 20, 30, 2, 5. Okay, so the same things that we solved. So 6 times 2, 5 is 0, 6. So matrix of T with respect to these two, this basis 1 comma minus 1 and 2 comma 5 is minus 1, 0, 0, 6. Okay, but these two are not orthonormal, right? They're not orthogonal. So if you take a dot product here, so if you take a dot product with 1 comma minus 1 and 2 comma 5, you end up getting 2 minus 5, it's minus 3. So they're not perpendicular. So how do you get an orthonormal basis now and make it see what happens? You can do Gram-Schmidt on this. So, you do Gram-Schmidt on this, you will get u1 to be the normalized version of this. So, it is just 1 by root 2 1 comma minus 1. Okay. So, what about w2 here? W2 is going to be 2 comma 5 minus inner product with u1, right. So, 2 comma 5 is all real. So, it is very nice. So, you do not have to worry about conjugate. So, if you do 2 comma 5 dot product with 1 comma minus 1, just now I did it, it is minus 3. So, minus 3 times, well, of course, you have to do a root 2 division, okay, because that is u1 is now this, and then I get a 1 by root 2 1 comma minus 1, that is u1, right. So, the dot product will have a root 2 also, and then I have a root 2 also. So, if you do this, I get 2 comma 5 plus 3 times 3 by 2, right, 3 by 2 comma minus 3 by 2. Okay. So, that ends up being 2 plus 3 by 2 is 7 by 2, 5 minus 3 by 2 is also 7 by 2. Oh, how nice is that? So, that ends up being 7 by 2 1 comma 1. So, now you can normalize, it is very easy to normalize this. So, you will just get 1 by root 2 1 comma 1. Okay. So, this is very nice. So, the orthonormal basis with respect to this is just became 1 comma minus 1 1 comma 1, of course, normalized with root 2 root 2. Now, if you find the matrix of this guy, matrix of T with respect to u1 u2, what will be matrix of T with respect to u1 u2? You have to find what happens when u1 goes into this. So, that is very easy to find down, right. When u1 goes through the matrix, u1 is an eigenvector, right, its eigenvalue minus 1. So, it will be minus 1 0, that is very easy. Okay. Now, when u2 goes through it, something else will happen. So, what is the matrix? It is 1 2 5 4. When u2 goes through it, which is 1 by root 2 1 by root 2, you are going to get something else. What will you get? You will get 3 by root 2 9 by root 2, right. This is what you are going to get. Now, what are the coordinates of 3 by root 2 9 by root 2 with respect to u1 u2? You do not have to solve any linear equation, you can just take a dot product. You take dot product of this with u1. Okay. What is the dot product of 3 by root 2 9 by root 2 with u1? So, that is what you have to find out. So, let us do that. Dot product of, so maybe I will just write it in a very simple way. So, 3 by root 2 times 1 3 is, right. It's just an easy way to write this. So, you will get dot product with this guy, you will get a 3 by 2, right. Those two are the dot products of 1 comma 3 with 1 comma minus 1, that will end up being 1 minus 2, right. 1 minus 3 is minus 2. So, you get minus 3. Okay. Similarly, if you take a dot product with this guy, you will get a 3 by 2 dot product with 1 comma 3 and 1 1, that ends up being 4, which is 6. Okay. So, basically you can check that this guy is 6 times 1 by root 2 1 comma 1 minus 3 times 1 by root 2 1 comma minus 1. Okay. Hopefully, it is correct. 6 minus 3 is 3, 6 plus 3 is 9. Okay. Very easy. So, once you do this, it is 6 minus 3. Oh, no, other way around, sorry, 3 minus 3, 6. Okay. So, of course, this entry has to be 6, right. The eigenvalues have to come on the diagonal value, but this becomes non-zero. Okay. So, this is an interesting little situation. What happened here for us is this is more general matrix. We found the eigenvectors, they were not orthogonal. We got a diagonalization with respect to a non-orthogonal basis. When you did this Gram-Schmidt orthonormalization, you also got an upper triangular matrix. Now, this non-diagonal entry did not become 0. You got an upper triangular matrix. So, with respect to an orthonormal basis, an upper triangular matrix is always guaranteed. But in some special cases, it seems to be also diagonal. Okay. So, this is an interesting thing. We will study all these things later on. But this is how one can expect it to be. Okay. So, there is another problem here which further works on this. There is a matrix of an operator T with respect to a non-orthogonal basis, it is diagonal. What will be the matrix of T with respect to an orthonormalized version of the same basis? Okay. So, first find the basis of matrix of T with respect to the canonical basis, it is sometimes easier, and then go through the orthonormalization, find out what the matrix is, you will get an upper triangular matrix. Okay. So, that concludes our study of orthonormalization and orthogonal basis. Thank you.